Our last major stop that we'll be stopping at on our way to modern quantum theory is a model that Niels Bohr came up with to model the hydrogen atom. So as we saw earlier in our video series, the spectrum of hydrogen definitely has some sort of quantum component to it, right? We see individual lines, spectral lines that are observed in the hydrogen atom spectrum. And so there's evidence of quantum behavior there. And Bohr wanted to understand, how could we model this? One thing I'll note is that this is wrong, this model that Bohr came up with, but it's a useful kind of stepping stone to show how scientists were trying to go from the classical ideas that we had to understanding these quantum objects, right? And so this picture of the atom is not right. We will go over the correct model of the hydrogen atom, the way it's understood at least nowadays, and that was developed, later after Niels Bohr. But this, like I said, can be a useful stepping stone, sort of understanding, how scientists were thinking about these things and trying to incorporate the quantum nature of particles and this wave idea into their models of the world. And so this was the idea that Niels Bohr had, right? We know that at this point they knew that hydrogen has a nucleus that has one proton, and there's one electron that is around that nucleus in some sense. And Bohr's idea is that we have sort of an orbit, right? We have an electron orbiting that proton, the single proton that's a hydrogen nucleus. And so then the question is, how can we take what we know about, charges, positive and negative charges, and understand what's going on here? And so what force holds that electron there? Well, the fact that we have a negative charge and a positive charge means that it's the Coulomb attraction, right? So this electron and positive and negative attraction to each other, known as the Coulombic attraction. And that Coulomb has, right, so the Coulombic force has a law that describes it. This is described in Maxwell's equations in classical mechanics. And the force is equal to the square of the charge of the electron. Well, this just happens to be because the electron and proton have the same charge, and that we have this 4 pi epsilon naught. That's mostly just a unit conversion factor, but it depends on 1 over r squared, r being the distance between our two charges. And so we have that force holding the electron there. Well, so if we just kind of only had that force, what we would see is that our electron orbiting the nucleus would get pulled in towards the nucleus, and then they would combine and you wouldn't have atoms anymore. And obviously that isn't what actually happens. This is part of the failure of classical mechanics, is that doesn't happen. So there must be some force keeping the electron from crashing into the nucleus. And so Bohr's model is that, well, it's the force that's keeping it from crashing into the nucleus is a centrifugal force. So the force, this is just the force that keeps any orbiting object going around in a circle around an object. And this force is given by the mass of the object times its velocity squared divided by r. And so these two forces have to balance each other. And so we can say that this force, number 1 here and number 2 here, if one of them was bigger than the other, the electron would either go towards the nucleus or away from the nucleus. And obviously neither of those is happening, so they have to be equal to each other. We have balanced forces here. And so we can say that we can equate these according to Bohr's model here. This Coulomb force, E squared over R squared, is equal to the centrifugal force, MeV squared over R. Now, there's an implicit assumption here that R is fixed. And so Bohr assumes R is fixed. And not only that, R has to be fixed such that the electron, he assumed that de Broglie was right, the electron acts as a wave, but this wave has to fit around, a specific orbit around the nucleus. So R is fixed, and it has to be at, these oscillations of the electron, which kind of represent this figure from your textbook, right? So this is going around the nucleus. It has to go around such that it fits around the nucleus in a circular orbit, right? So if we have, say, an electron where the wavelength doesn't match up, if it doesn't match up, if we continue that, we get destructive interference. And if we get that destructive interference, Bohr assumed those orbits don't work. And so in equation form, the way this has to work is that the circumference of this orbit, 2 pi r, is equal to some integer number of wavelengths, n times lambda, where n is equal to 1, 2, 3, ... And so we can then use the de Broglie wavelength formula that we had from our last video, lambda equals h over mv. Let's fix that. mv, there we go. And we can plug this in. So 2 pi r is equal to n times h over mv. We can rearrange this and get that we have mev times r is equal to nh over 2 pi. We can make a substitution here. This is a substitution we'll use a lot in this class. H over 2 pi we call h bar, because this shows up all over the place in quantum mechanics. So we can say this is equal to n h bar. Okay, and so this MEVR that shows up on the left-hand side of this equation, this is the angular momentum of the electron spinning around in its orbit. And the assumption that Bohr makes here is that the angular momentum has an integer component here. This is, yet again, another quantum effect. So Bohr is implicitly saying that we say quantized. The angular momentum is quantized. It comes in discrete amounts that are in units of h bar. So you can have angular momentum equal to h bar or 2h bar or 3h bar, but you can't have half an h bar or 2/3 of an h bar. It can only come in integer amounts. And so this is the quantum part. Bohr is implementing quantum mechanics a little bit into this model here. We'll continue this in the next video, but I'll go ahead and pause this video here.